concatenate, torch, reshape, concatenate, torch, reshape. Oh, hey, I didn't see you there. Have you ever wondered what a trumpet sounds like? What about over there? Or maybe up there?
I too want to know what a trumpet sounds like, because I clearly can't play one.
Well, you're in luck, because we've developed a revolutionary new technology that can use just a few measurements from the space to reconstruct the entire 3D sound field.
Let us show you how it works.
Alrighty, while this technology might not be revolutionary yet, it is helpful and useful. However, it doesn't really teach me to play the trumpet like Louis Armstrong. So, let's get into it. According to the Nyquist-Shannon theorem, a complete acquisition of an acoustic environment requires dense sampling across the area of interest, typically one measurement every half centimeter. This could be quite prohibitive, so, to reduce this measurement requirement, we want to upsample sparsely collected data using deep learning techniques. And the applications of this are many. You can use it for accurate audio representation in VR and AR systems, as well as better acoustic modeling and noise source identification, which is prevalent in many fields.
Here's a brief overview of the data we used. It comes from work done by Koyama et al. In their work, they used 3,969 microphones, shown in this figure to the right, to take nearly 33,000 pressure measurements per microphone over a time period of 0.68 seconds. Together, this data constitutes a room impulse response, or RIR, for every microphone, an example of which is shown in this bottom left figure. As this figure shows, RIRs contain data about not only the source sound, but also any echo and reverb due to room geometry. We used a low-pass filter to isolate only the source sound from the RIR data, as that is what we want to reconstruct. For our data preparation, we are struggling with some hardware limitations here. We can't use the entire data set, so we downsampled. We used 125 evenly spaced microphones over the entire domain, as we showed in this figure here. At each microphone, we only used 800 time steps, and we made sure those time steps were evenly distributed throughout that 0.68 seconds. We use a unique activation function that we'll describe later, but for that, we also needed to scale our data and normalize it. So we normalized our time between -100 and 100, and we did the same thing for position, except for between -1 and 1.
So with that background and with that data structure, here is the model. It is a physics-informed neural network from Olivieri et al., and this model incorporates a 3D wave equation for the physics loss and a unique sinusoidal activation layer called siren, which has variable initialization frequencies. So just jumping into this, a siren layer stands for a sinusoidal representation network. It's a linear layer with a sinusoidal activation function that can be seen over here on the right, where your input vector and your weights and biases are all wrapped within a sine function. A unique thing about this is that your initialization frequency, which is this omega naught, that can be changed and adjusted for each layer. This does a great job at capturing and predicting frequency-based data, whether it's high frequency, low frequency, and this is something that can be fine-tuned to a specific data set. And you can see here the difference between the siren layer, a hyperbolic tangent, and a ReLU in reconstructing this image. So it's something that works really well for this data set.
So here's some more details about our multi-layer perceptron model. This model uses 4 inputs. 3 of them are microphone position in X, Y, and Z. We also have a time vector, which just describes where in our 800 time steps we're looking at. These inputs go into 3 hidden layers. These hidden layers are all siren layers. So our initial one is a siren layer with an initialization frequency of 30. Our second one is 15. Our third is 10. And our fourth is 3. These initialization frequencies are experimentally determined to best match our acoustic frequency response data. These all combine then to output a pressure at the given time and location. Something that is worth noting is that our initialization frequencies that we just described are in disagreement with the paper that we've previously described. The paper suggests that the first layer should be a 0.5 initialization frequency and subsequent layers should be 30. We tried this, we could not get it to work. We were not close to getting it to work. So as we looked more into this, into other papers that use siren, we found that this is not really a common approach. We went back and found the original siren paper by Sitzman et al., and we found that their recommendation of starting at 30 and working your way down really performed much better. And we're actually curious if this was a potential print error in the journal that we originally cited.
With that, for our loss function, like we mentioned, it's based off of two components. We have our data loss, which is based off of training data, and for that, we just used a mean squared error. We also have our physics loss, which is based off of the 3D wave equation applied to all the pressures. That equation can be seen in the bottom right of the screen, where N is the predicted pressure from the neural network, and everything in the parentheses on the left side, that is the wave equation applied to the pressures. In this, it's important because we had to scale the speed of sound to our normalized data, and that used the x-scaled and the t-scaled values that we calculated earlier. We also did 2,500 collocation points that were sampled through a Latin hypercube, and then we used Torch AutoGrad to compute all the gradients for this. An interesting thing with this is we had to scale the physics loss down by about 1e to the -5 for our total loss function to converge and for us to produce good results. So with the model in place and our data in place, our approach to making this all work included 4 steps. The first one was to start with a small data set with just a few time steps. For this, we just used the bottom plane of these 5 planes, and our goal was to first fit the data, then add the physics loss. And once both of those were working, we would then increase the number of data points used until we were using the whole set. Then we created a test data set to test the model. And lastly, we explored other models such as a neural ODE with an autoencoder and compared results with that.
So jumping into that first step where we used a single slice with 5 time points. We batched by time point, so each of those 5 time points, we had a batch of 25 corresponding to the number of microphones. We quickly want to describe this figure on the right here. It'll be similar ones will be coming up throughout the presentation. So first, on the left, we have the actual pressures, and on the right, we have the predicted pressures. The X and Y just show the position. Each rectangle is a microphone, and the color of that rectangle represents the pressure of that microphone, which is then shown on the color bar there. So in the perfect world, we'll have the actual pressures and the predicted pressures matching exactly. You can see here that we're doing pretty well at this point when we're just training with all of our data. So once we decided to start adding our physics loss in. It was a little bit of a pain at first, but eventually we got it to match pretty much exactly the plot I just showed you. Our loss plot did get a lot more interesting though, so we want to touch on that real quick. We do get these really interesting spikes in our data loss when we split it up into data and physics. So when we add the physics loss, we start getting these spikes, and we think that that is probably because as our physics loss trains and it changes the weights and biases, every once in a while it moves in a way that might satisfy the physics loss term better, but it makes a significant difference in the data loss, and we get this big spike. As it goes through this process, it adjusts the weights and biases, and it just overall ends up remedying this discrepancy. And we can see that as we get this overall decreasing trend, even in our physics loss and train loss.
With the physics loss and data loss working, we decided to start increasing the number of data points we were using. We first did this by increasing the amount of time points we were using, and that can be seen in this picture right here on the right, the results from that. In this, we focused on the 208th time step because this is the most prominent part of the wave and the area of the wave that is of the most interest. This also corresponds to where the wave has the highest gradient values. And so in this, we can see that we produced a near exact replica for the predicted pressures to the actual ones, and our loss plots seem to converge to a relatively good value. So then we decided and slowly worked our way up to using all of the data points in our training set, and these are the loss plots for that. Our loss plot converged down to around 10 to the -7, which was a good threshold for ensuring that we were going to get good and predictive results. Training this model for 3,000 epochs took nearly 3.5 hours on a GPU, so it took a long time, but our results are pretty good. This is once again at the 208th time step. Each column corresponds to a Z-plane or a slice of data, and the top row is the actual data, and the bottom row is the predicted data. And from this, we can see that we are matching the actual with the predicted data pretty well. However, when we go to time steps that are further away from the prominent peak of the wave, then we notice that the data becomes less agreeable between the predicted and actual sets. This could likely be due to smaller gradients and flatter parts of the wave. However, we noticed that as we trained it longer, this became more accurate. So we anticipate that if we train this model for an additional few thousand epochs, we would be able to reproduce this data pretty well.
So now that we've shown that we can match our trained data, we want to start testing our predictive power. The first way we did this was by adding slices in Z. So as you can see in this figure, we added one slice between each of the 5 already there. And here are some of our results. In this area, again, the time index of 208 that we're most interested in, we can see that we pretty much nailed it. The way this plot works is that each column is one of the slices that comes between the original training slices. So none of the points here were used for training at all. And we're really happy with the results here, and we're really impressed and pleasantly surprised. Here we see similar problems to our previous training, just that when we're not in that really clear gradient region, we just have really messy data and really messy predictions. The second way we tested was by removing some of the mics in the slices. We would have liked to do this in the entire data set, but hardware limitations again. But the way we did this was in one slice, we tried using just 90% of the data for training and then 10% for testing. And then we did the same for 75-25 and 50-50. So here are the results for the 90-10 train tests data set. We can see that it really matches pretty well. This would be useful and predictive, and you can see that there might even be room for improvement in our loss plot, as we can see that the test loss is continuing to go down. But overall, it did perform quite well. For the 75-25 train test set, it's a little bit worse, and to get here, we did have to make some changes. We added an additional siren layer, and we had to use 1,000 more epochs. Overall, though, this would still likely be useful. We're still pretty happy with how it worked, and we do have room for improvement should we be willing to spend the hardware and time to continue training. 50-50, you can really start to see some problems. There's a lot less similarity between the predicted and actual pressures. There's still probably some room for improvement by continuing to train or by using a little bit beefier model with more layers or something like that. But we could not get it better as we worked through this.
So the last thing we did is we created a neural ODE with an autoencoder to compare against the results we got from the pin. And so just a brief overview of this, we did a single layer autoencoder with a latent dimension of 32. We tried varying the learning rate from 5e to the -5 to 1e to the -3. We also tried multiple activation functions. We used siren layers. We also tried linear layers with an inverse tangent or hyperbolic tangent function. And this required significantly longer time to train, both in terms of epochs and minutes, and overall it produced less favorable results. This slide kind of shows that is this took about 5,000 epochs to get some data that is slightly worse than what we got on the pin. And when we did tests where we only trained it for 2,000 or 3,000 epochs, the data was much worse. And so while this is still a viable option, we think it's less efficient than the physics-informed neural network.
Now, from this work, we've drawn a few conclusions. First is that based on this project, with the known dynamics of the wave equation, we think a pin is just a better option than a node. It trained faster and it gave better results. We also think that overall our implementation of a pin was successful. We were able to replicate the 3D sound field measurements based on the wave equation, and we do have room for improvement. We think that we could further refine the model by training for more epochs, by training different hidden layer counts, by fine-tuning the batch size and initializing frequencies, but a lot of this would require more computational power. We'd also like to try to compare our pin to a convolutional neural network. We think a CNN could be particularly useful here, since this is easily visualized data. Finally, thank you for watching, and if you have any more interest in the topic, here are the 3 sources that we used. Hey, man.
What's up?
Did you ever get the model to work?
Yeah, I think I did, and it worked pretty well.
But did it teach you to play the trumpet?
You know, that I should have trained more.